Hear that? What force is in play when a speeding train screeches to a stop? What major force is in play when someone jumps out of a plane? We're in Blue Ridge, Georgia, where in this segment we'll explore two types of forces that happen all around us. First one is the force in play when train wheels come to a screeching halt on a steel track. What force is that? Well, it's the same one that happens when an ice skater stops cold on a sheet of ice. If you said friction, you're correct. Friction is written F sub F. Friction happens when one object rubs against another and there's some resistance between the two. So friction is the resistive force between an object and a surface. Friction can occur when both of these objects are at rest. That's a type of friction called static friction. It's the force between two objects that resists motion. Another type of friction happens when an object is in contact with another object and one or both of them are moving. That's kinetic friction. Let's start with static friction. What do you think causes it? Look through an electron microscope. You'll see at the molecular level that surfaces of all kinds have bumps and ridges, some more than others, so they can grab onto other objects, creating static friction, even when there's no movement at all. Moving a heavy object like a crate is a great example of static friction in action. It's hard to do at first because microscopic bumps and ridges in both the bench and the crate are actually gripping to each other. Once you get it moving, it's easier to move because those bumps and ridges don't have time to connect to each other. Static friction is written F sub S, not to be confused with spring force, which is also written F sub S. You'll know which one to use based on the problem you're trying to solve. Static friction only happens if an object and the surface are at rest relative to each other. An object on a flatbed truck is subject to static friction even when the truck is barreling down the highway. But if the object starts sliding around the flatbed, then kinetic friction is in play. Kinetic friction, written F sub K, happens when an object is moving. To help explain kinetic friction, let's go back to the moving train. As a train slows down, the brakes exert a force called kinetic friction on the wheels, causing them to rotate more slowly. The brake drum and the wheel are in contact with one another and slide against one another. Kinetic friction. Rub your hands together real fast. You're creating kinetic friction, and that creates heat, F sub K. So what affects the amount of friction between two objects? An important factor to consider is what the objects are made of, how much they grip each other at the molecular level. And it also depends on the normal force acting on the object from the surface. It's written F sub N. Remember, some surfaces grip more than others. The gripping action has already been measured and a number has been assigned. That's the coefficient of friction. You write the symbol like this, a U with a tail. It's the Greek letter mu, and mu stands for the coefficient of friction. So the coefficient of friction between two surfaces depends on the type of surfaces. There are standard tables that have it already figured out for you. For example, when rubber meets rubber, it has a friction coefficient of 1.16. When steel meets steel, there's a coefficient of 0.74. Where ice rubs against ice, there's a coefficient of 0.1. Not much friction there. But how about steel on ice? Check out the table and see what you find. Keep this in mind. The force due to static friction is always less than or equal to the coefficient of static friction times the normal force. So figuring out how much frictional force is going on between the crate and the bench, think about two things. The coefficient of static friction, mu sub S, and the normal force of the crate, F sub N. So when a crate is at rest on the bench and you try to move it, it takes a certain amount of force to get it moving and to overcome the frictional force between the crate and the bench. The reason for the less than or equal sign is because you can only exert a force up to a certain point, the amount of the force that's equal to the coefficient of friction times the normal force, before the static friction becomes kinetic friction and an object starts sliding. Once your crate is moving, the kinetic friction force is F sub K, which is equal to the coefficient of kinetic friction, written mu sub K, times the normal force, F sub N. Okay, let's look up at the sky. Which forces do birds, skydivers, airplanes, and my hand out the window of this train have in common? They all have to deal with drag. It's another friction type force. That's why it's written F sub D, and it's commonly known as air resistance or drag. Put your hand out the window. You can feel the air resistance. It's like your hand is swimming in the air. And the faster you go, the more drag blows your hand back. We'll talk more about this force in another segment, but know that it's a form of friction. So do you remember Newton's second law? Objects will accelerate in the direction of the net force acting on the object. So net force equals mass times acceleration. Forces are measured in newtons, mass measured in kilograms, and acceleration is meters per second squared. With that in mind, let's figure out this problem. And remember to use significant figures. Greg pushes a 20-kilogram box across a surface with a constant force of 100.0 newtons. The coefficient of kinetic friction between the box and the ground is 0.4. What is the magnitude of the normal force? And how fast does the box accelerate? First step, draw a free body diagram. Box, normal force arrow up, gravity force down. On the y-axis, the box is not accelerating. It's not moving up or down. They are balanced, so the arrows are of equal length. Now, draw an arrow representing the applied force and one representing the friction force. Next step, pick your positive directions. For this problem, positive will be up and to the right. That will be the case for 99% of the problems we solve. Next, figure out the normal force. To do that, look at one dimension at a time. Let's look at the forces acting in the y direction. The box is at rest in the y direction, so we know we aren't accelerating in that direction, so normal force and the force of gravity are the same. So the net force in the y direction is 0. This means that in this problem, force due to gravity is equal to normal force. In another segment, you learned the force due to gravity is the weight of the object, and force due to gravity equals mass times the acceleration due to gravity on Earth. The object has a weight which is equal to its mass, 20.0 kilograms, times the acceleration due to gravity on Earth, or 9.80 meters per second squared. So the normal force is equal to 196 newtons. Next, let's solve for the acceleration of our box by looking in the x direction. Our net force in the x direction is equal to m times a, since we aren't at rest and the problem doesn't say we are moving at a constant velocity. There are two forces in the x direction, our applied force of 100.0 newtons to the right and the force due to kinetic friction to the left. To find the magnitude of our frictional force, let's recall our equation. Force due to kinetic friction is equal to our coefficient of kinetic friction times the normal force. So kinetic friction is equal to 0.4 times 196 newtons, or 78.4 newtons. Now that we know the normal force and the force of kinetic friction, let's go back to the original equation. Net force equals mass times acceleration. When we fill in the forces that are acting in the x direction, we see that the applied force minus frictional force equals mass times acceleration. We know everything here but the acceleration, so let's figure that out. The applied force is 100.0 newtons minus the force of friction, which is 78.4 newtons, which equals 20.0 kilograms times the acceleration. Subtract 78.4 from 100. You get 21.6 newtons, and that is equal to 20.0 kilograms times acceleration. Solving for acceleration, divide both sides by 20.0, and acceleration is 1.08 meters per second squared. So whether it's on the ground or in the air, friction exists as one of those forces you have to consider when you're at rest or on the move. That's it for this segment of Physics in Motion. We'll see you next time.
For more practice problems, lab activities, and note-taking guides, check out the Physics in Motion Toolkit.